All right, so we should see a little red flashing light in the top left hand of our Zoom screens, which means we are recording. And I will hand over the floor to Group 5 to share with us their design.
Thank you. So first of all, good morning, everyone. Thank you for attending our presentation this morning and allowing us the opportunity to share our work this semester. We would like to first thank our professors, Dr. Trom and Dr. Mimi, as well as our TA, Francesca Lopez, for their support and guidance. We would also like to thank the corporate sponsors, Northrop Grumman and Cummins, for their support of engineering education. So we are Group 5, and we will be presenting the Vulcan Innovative Bioreactor System. And so the name Vulcan comes from the Roman god Vulcan, who was the god of innovation and technology. And so this next slide here displays our contact information, should anybody need access to it. So we will begin our presentation by briefly discussing how our different subsystems work together to create one cohesive machine. We will then transition into a brief description, or excuse me, a detailed description of each subsystem, highlighting key details and relevant mathematical calculations to justify certain design choices. We will conclude our presentation by discussing the technology readiness levels for our different subsystems, as well as general features of our products, such as the cost to prototype.
So this is our microbioreactor. As you can see from the picture on the left here, we have a door that allows the user access to the conical tubes, shown, which would be in the compartment on the front. And then there's a separate door located on the back, which you can't see from this picture, and that allows the user access to the well plates. And this isn't apparent from the center picture because we've hidden the walls such that you can see the inner workings of our microbioreactor, but there's a wall splitting the environments that contain the conical tubes and the well plates. This gives us individual control over the environments that the conical tubes and the well plates are in. And it's also why we have two separate liquid dispensing systems. For our liquid handling systems, they move along this truss as seen at the top of the middle picture, and they can also move up and down such that they can reach the conical tubes and the well plates and dispense liquid appropriately. There's also a third degree of motion that is given to us by this track down beneath the conical tubes and the well plates, and that allows us to move the conical tubes and well plates back and forth such that we can reach, the liquid dispenser can reach all of the wells and tubes. And then over here on the far right is our HVAC system, along with some components of our user interface that you can see inside here as well. Next slide.
So what makes our design unique and different from the others? So first of all, our passion. We are passionate about creating an autonomous microbioreactor that is also very universal and can be used in a wide range of different labs with different types of experiments. What makes our design different is our state-of-the-art HVAC system, which was intricately designed. And lastly, we are economically driven. So we used primarily OTS parts and made cohesive design choices in order to minimize cost, which enabled us to come in under budget. Next slide. So now that we have done kind of an overview of our system and how it works, we're going to go into the specific details of each subsystem.
So this is our structural housing. As you can see, it consists of a structural frame as well as the insulation shown on the right. The main components of the structural frame are made up of 304 stainless steel rectangular tubing. And we picked 304 stainless steel primarily because of its good heat resistance and corrosion resistance. That's also why it's most commonly used in lab equipment in general. The studs are used to support the walls and the roof of the microbioreactor. And then we've got this truss here along the top that's used to support the liquid handling systems that move back and forth across the well plates and the conical tubes. If you go look over at the right, you can see the individual compartments that we're placing some of our systems in. So this big compartment over on the right side of this picture is for the HVAC housing. Then you have the well plate housing and the conical tube housing. This sort of intermediate boundary layer that you see in between the compartments is the insulation, which is made out of fiberglass. And then we've got an LED strip here, and it's also on the other side. You just can't really see it from this picture. And that's used for any sort of microbial process involving photosynthesis. Next slide. So for our structural housing proof of concept, we needed to determine how thick the insulation needed to be. And so this is a cross section of our wall. So we have these very thin sheets of stainless steel. And in between those sheets of stainless steel, we have the fiberglass inserted. And then we have the polypropylene that sort of is the outer casing of the machine for a cost-effective and professional finish that's also easily manufacturable. And to determine the thickness of insulation that we needed for like the stainless steel sheets, the fiberglass and the polypropylene, we just you set up a simple thermal circuit to figure out those calculations. Next slide. And then our additional proof of concept was to ensure that the truss above the that's supporting the liquid handling system was going to be able to support the weight of those systems. And so we just set up a simple static analysis for each of the individual sides, and which happened to be identical, and a load P with a varying position A. And we were able to determine the maximum tensile or vice versa compressive stress that's being placed on the beam is only 2,087 PSI, which is significantly less than the yield strength of the material we have chosen. Next slide.
So our environmental control system was designed to control the temperature and gas composition within each chamber separately without mixing any of the air within those two chambers. This is thanks to the system of inline fans and check valves that control the airflow into and from the separate chambers, as well as to and from the air conditioner. The ducting that is used is made of temperature resistant rubber ducting with a few stainless steel components that have fiberglass insulation attached to them to prevent any heat from escaping into the HVAC compartment. Now, the HVAC system meets BSL-2 requirements by creating a sealing effect with the doors. So on the doors themselves, there's a rubber that is pressed flush against the side using a door lock, as well as a filter box containing a MERV-11 pre-filter and a HEPA filter to capture biological agents and any hazardous particles that could possibly contaminate the laboratory airstream. Now, the air that passes through the filter box will be sent out of the device and into the laboratory HVAC system. Both chambers contain a dual temperature and relative humidity sensor and gas sensors that are capable of detecting the 5 primary gases required by the customer needs. Both chambers also include a PTC heater with a fan capable that is oriented so that its fan sucks in the cooler air from the bottom, heats it up, and passes it out at a higher temperature upwards. Now, for gas management, there are 5 ends of tubing that stick out of the device that can be hooked up to any gas tank. Explosion-proof solenoid valves were utilized for tubing for combustible gases, of which there are 3 predicted in our customer needs, as well as the 2 tubes that lead to the chambers, as it has been proven in industry that previously experimented with solenoid valves that were not explosion-proof tended to explode when exposed to combustible gases. Next slide. First of all, the cooling load calculations were done by taking the chamber by treating it as a cooling room. So several factors were accounted for, including the heater fan motors, the shaker motors, the liquid handling motors, chamber volume, and the LED lights installed for photosynthesis, and the LEDs for the ODFI section were considered when developing these calculations. Once those calculations were complete, it was discovered that the cooling load for the tubing chamber was 404 watts, and the cooling load for the well plate chamber is 442 watts. Since our AC unit is rated for a cooling capacity of 450 watts, it should be able to cool both chambers regardless. And to calculate the heating and cooling times, we conducted a lumped capacitance heat transfer analysis for forced convection of hot and cold airflow, and utilized associated formulas to determine that the heating time was 6.2 minutes and the cooling time was 4.9 minutes. Next slide. Now, to determine the orientation and the placement of our heater, we conducted a flow simulation to see how it flows within our chamber at different heights in order to ensure that we set it at a reasonable height within the chamber so that all the cool air can be properly sucked in. And we determined a range of between 75 to 125 millimeters higher from the inside chamber floor, which should be sufficient to heat the system. Next slide.
So for our liquid handling subsystems, we actually have two subsystems, one for the well plate side and one for the conical tube side. They are almost identical. So they use shaft rollers that roll along a rail that is connected to the ceiling of our bioreactor. They also use NEMA 17 high precision motors, which are capable of a step size of 0.9 degrees rather than the traditional 1.8 degree steps for stepper motors. They function using two lead screws. So the first lead screw in the back moves the entire system up and down in order to reach the cultures. And then the smaller lead screw in the front controls the plunger on our syringe. And our syringes also have a lure lock design, which enables the user to switch out the needle as they see fit based off of their experiment. Now, what makes the two subsystems different are the syringes that we used. So for the conical tube side, our syringe has a capability of dispensing 20,000 microliters. And then for the well plate side, it can dispense 2,500 microliters. And we did this because we found that for the larger syringe, we were only capable of having a resolution of 0.5 microliters for dispensing liquid. And we figured that in order to make our system more applicable for more experiments, we might want to decrease that. So for the well plate side, our syringe can dispense 0.6 microliters per step. Next slide. So within each chamber, we have these three wells. And so our needles are designed to be used throughout the entire 2-week incubation period. And so in order to sterilize them, they would travel over to the well that contains the sterilizing solution. We used isopropyl alcohol. It would dip into it, suck a little bit up, and then dispense it into the waste compartment. And we expect that since it's an alcohol, it'll evaporate almost instantaneously, leaving our needle sterilized. The other two wells include cell medium in case that needs to be accessed. And then the third one is a waste compartment, which has a hole in the middle that has a tube that connects to a valve on the outside of the housing to properly dispose of our waste. Next slide.
So for our liquid handling proof of concepts, our first calculation is our volume flow rate. So we were able to meet the customer need of 300 microliters per second by performing a control volume and conservation of mass analysis on both syringes. Secondly, we were able to meet the processing time of 15 minutes by finding the amount of time it would take to dispense liquid as well as do OD and FI measurements. We did it on a 384 well plate, which is a 12.9 minutes, which has the most wells in order to give the most conservative number. Lastly, our dispensing accuracy. We were able to meet the tolerance of 0.1 microliters for up to 11.9 microliters of volume. Beyond the 11.9 microliters of volume, we were able to meet a 1% tolerance. Next slide.
So this last calculation that we did actually came from questions that we got during our poster symposium. around concerns regarding the deflection of our liquid handling system. So we performed this calculation using a simple cantilever beam analysis, and we found that the deflection would be only 0.0004 millimeters, so we don't expect this to be an issue in use. Next slide.
As for the shakers, we have two shaker system. The first accommodates up to 3 well plates of any standard type. The second accommodates up to 10 conical tubes, 5 of them being 50 millimeter type, while the remaining are 50 millimeter. Both shakers can provide all 3 shaker patterns by implementing a system with 2 NEMA 23 stepper motors. Both motors are located on the cart that rides on the shaker rail. The first stepper motor provides the linear motion of the system along the cart using drive rollers, while the second motor provides the orbital motion of the system. The combination of these 2 motors will achieve any motion pattern. So if you like to use the linear, just use the linear system. The orbital, use the orbital. Combining the 2, the linear and the orbital, will produce the double orbital motion. Additionally, the ODFI measurements, there are several ODFI PCVs below each of the well plates and conical tubes. These are used to illuminate the samples when the ODFI samples are being measured. Next slide, please. To eliminate the possibility of spilling the samples during the shaking process, a sealant film is used on the well plates via an adhesive. These seals are pierceable by the needles and has a self-generation quality, which allows us to use them multiple times. Additionally, the sealing is also permeable, so the ambient environment can reach the samples with no problems. Next slide. For a proof of concept, the first calculation we made was to find the maximum linear operational speed of the shaker, which was found to be 49.088 inches per second. This basically tells us how fast the shaker can travel along the rail. Using the results and an operating frequency of 10 hertz, we calculated the path length. The path length is basically the direction that the shaker needs to travel to ensure that it operates within that frequency. We also, to prove the maximum operational frequency of the rotational motion, which is also 10 hertz, is synchronized with the linear motion. The final calculation shows that the 2 motions are indeed asynchronous. Next slide. To ensure that the well plates will remain secure in the shaker throughout the operation, we had to account for the centripetal force acting on the well plates. So we calculated this force to be 51.86 newtons, or 11.66 pound force. Next. And essentially, to deal with this, we had to account for the opposing force. So we use a spring force to counteract the centripetal force. And using a simple calculation with the change in length being of 0.4 inches, we found that the necessary spring constant of 28.9 pound force inch. And therefore, a spring constant of 35 pound 4 inch was selected to make sure that the wells remain in place throughout the operation.
So our ODFI measurement system is broken into 2 parts. The first part in the left image there is our measurement arm, which houses the sensor that we will use to measure the incident light and the intensity. The image on the right is our LED array, which will provide the initial intensity in the initial light. So first, starting with the measurement arm, the measurement arm itself will be mounted to the liquid handling subsystem. And so therefore, there will be 2 of them in our final design, 1 for each chamber. And the justification or the reasoning behind choosing the to mount on the liquid handling is that the liquid handling system has to reach every well plate, and every tube. And so by attaching the ODFI measurement system there, we can ensure that it can also reach every well and tube. And because it's attached to the liquid handling system, we wanted to ensure that it was a relatively lightweight system. And so the material choice in this case was we chose to use a polypropylene 3D printed plastic. It's very lightweight, it's easy to manufacture, and perhaps the most important part is in the case of a spillage or if any sample gets on this material, it can be autoclaved and cleaned to ensure the BSL2 standards. And so the principle of the operation of the measurement arm is that it will be raised and lowered with a 5-volt DC stepper motor, as you can see on the left there. Now, again, because it's mounted on the liquid handling subsystem, we want to ensure that while we're dispensing and taking in fluid in this syringe, that the ODFI measurement system does not get in the way or interfere by bumping into any tubes or well plates. And so that was the reasoning behind placing a 5-volt DC motor there. The measure sensor itself is a phototransistor, which will be wired to a reverse biased PCB board to correlate the voltage drop across the transistor with an incident intensity. It should be noted that a calibration step would be required, as this intensity measurement would be a relative measurement. Now, moving to the LED array itself, which will provide our initial light and intensity, we have opted to place an LED under every single well and every single tube. And as you can see, we have about precisely 384 LEDs for every well. And each LED is a full color LED, meaning it can reach it has a spectral range approximately equal to that of the visible light. This spectral range is practical for many fluorescent intensity measurements. And the largest intensity for these LED lights actually occurs at about 580 nanometers, which is perfect for optical density 600 nanometer measurements. And these will all be mounted to PCBs that will control the power across these LEDs and can then control the actual wavelength they emit at. And so because we're placing a LED under every well on the well plate, we want to ensure that for the smaller well number sizes, that we still have an LED under every well. And so clearly we satisfy 384 wells because we have 384 unique LEDs. But as you can see in the right image where we've made a 96 well plate transparent and transposed it on top of our LED array, that there is at least one LED under every well. And so these LEDs will be independently controllable. And so we can just light up one at a time, or in the case of the much smaller well sizes, the smaller number well sizes, we can illuminate a few at a time to ensure that there's no cross-contamination of measurement due to exterior lighting. And so for the smaller number sizes, such as a 24 well plate, it will be guaranteed that there will be at least one LED underneath those wells, as the distance between the two LEDs is approximately 6 millimeters, and the well diameter of a 24 well plate is about 14 millimeters. And as in one of the previous slides, I explained the measurement arm. And so to ensure that the measurement arm can actually lift the sensor in the arm itself, the motor can lift the measurement arm and the sensor itself, we did a motor torque calculation, assuming it was a cantilever beam with a load of magnitude F at the end. Now, this is a worst case scenario, as the load itself would be distributed along the beam. But using this approximation, we found that the required moment would be 0.009 Newton meters. And the motor that we chose to use was rated at 0.015 Newton meters under normal operating conditions. Finally, because we have a force in the moment applied to this to this arm, we wanted to ensure that the material that we chose earlier, polypropylene, would not yield under these stresses. And so performing a pure bending assumption on this beam and taking a cross section we were able to determine that the maximum tensile yield stress under this static loading would be 270 kilopascals, which is much lower than the 40 megapascal yield strength of polypropylene.
So for our user interface, it's just going to consist of a program running on a laptop, and then that laptop will be connected via a USB cable. That cable will go through this feed and then connect to a Raspberry Pi 4 Model B. That Raspberry Pi will then communicate with a power distribution panel that will govern these brushless motor controllers, which sort of helps control all the different subsystems and allocates power accordingly. In terms of e-stop, there's a digital e-stop button on the laptop program. And if for whatever reason that doesn't seem to work, we have also placed a physical e-stop button, as you can see in the left-hand picture, and that physically cuts off power to the microbioreactor, which so if anything occurs, so whatever safety reason might happen, and the digital e-stop doesn't work because, I don't know, like just say it caught on fire and the Raspberry Pi was destroyed, you could physically hit that button and kill the whole system. Next slide.
So as for determining the technology readiness level of our design and each component, we kind of did it in two different ways. So the first column is the more traditional technology readiness level. So since we haven't actually been able to build or test a prototype of our design, we're kind of limited to level 3, which is proof of concept just through design and calculations. However, in the theoretical technology readiness level column, we kind of extrapolated and we hypothesized what each subsystem would be if we could test it. And this is just based off of existing similar designs that use components of our designs in a functional manner that's currently on market. Next slide.
The total cost to produce our bioreactor was split into 4 categories. Beginning with the OTS parts cost, the approximate cost was about $5,854. The modified OTS part cost was $719. The raw material cost for manufacturing was $2,405. And the manufacturing and assembly labor cost was about $437. This sums to a total cost of $9,417.47, which is under the $10,000 budget. Lastly, the overall dimensions of the bioreactor are 66 inches in length, 37 inches in width, and 31 inches in height, which would fit on a laboratory benchtop. And the overall weight is 165 pounds. We would like to thank you all for attending, and now we'll be opening the floor to any questions about our design.
Okay. Thank you for the presentation. Any questions from our panel?
Yeah, I've got a quick question. So your well plates, do they have covers to address spillage?
Yes, sir. They have covers to address spillage. So in one of the previous slides, I believe it's slide 18. So where we're covering the functionalities of the shaker, there's this sort of, that slide. So there's this fine, very thin layered film that is covered over the well plates, such that if you needed to shake them at a higher RPM and you ran the risk of spillage, it will prevent cross contamination between the wells.
Okay, thank you.
You're very welcome.
I think that's a clever solution. This is Tom from Northrop Grumman. I think that's a clever solution. You mentioned that it's gas permeable. I'm wondering what your criteria for the gas permeability would be, because I mean, obviously different gases, different molecule sizes, and different requirements from your customer on that. So this is something where, you know, as opposed to a like physical lid that would be on top of it, you know, maybe while it's shaking can be removed. This would be on there for the duration of the experiment. So what is your customer's requirement for permeability here?
So that's an excellent question. I do not know specifically the answer to that. Our group mate, Zach, who really worked on this, would be a more appropriate person to have answer that question, but he is not here as a result of a family emergency. So I don't know a question, the answer to a question that specific, but I can check and get that answer to you as soon as possible.
Perhaps I can elaborate a little bit there. The customer needs themselves specified that we would have to control the composition of the air, 5 different gases inside the chamber. And so this seal here, this sealing film, it's a proprietary material. I believe it's called Aero Seal. And it allows, it's rated, or excuse me, the data sheet says it's very permeable for general air and carbon dioxide. And so we have made the design choice that this would be the most efficient way to provide a clear surface for optical density measurements so that they're not altered in any significant way, prevent spillage, and still allow for small fluctuations in the ambient enclosure atmosphere to be transferred into the well plates.
And the largest gas that will be injected into the system will be carbon dioxide that will be needed for experimentation. So that's also what influenced our decision for this.
Okay, yeah, it's one of those things where it's maybe such a novel approach to the problem of spillage that maybe it's something the customer hasn't anticipated even needing to write a requirement for. So that's something that, you know, my advice would be reach out to them and coordinate and see if that, you know, meets an unspecified need. But I do like it. It's clever, and it's the first one of these that I've seen through a number of different presentations, you know, going back to last semester. So I would ask, your system essentially doubles everything in it in order to be able to handle well plates and the conical tubes. Is there any ability to, you know, run tubes on the side that you're showing well plates, or run well plates on the side that you're showing tubes, or are all of those essentially incompatible?
So our shakers are designed separately. One is designed to hold the well plates, and one is designed to hold the conical tubes. I'm sure that plate could be customized based off the customer need in order to accommodate both, because they both perform the same shaker patterns. But as of now, it is designed to have well plates in one compartment and conical tubes in the other.
And there's no ability to transfer media from one side to the other?
No.
Okay. And while we got the picture up, I guess I have a number of questions about the well plate design. You've got what appears to be just a spring holding like radial centripetal force on the well plates. If this thing's shaking back and forth, I assume it's got some circumferential acceleration too. What restrains it that way, and why did you go with this sort of spring retention rather than like a more rigid recess to put the well plates in?
So for the shakers, there's a, it's really hard to see from this picture, but if you go, think closer, you can sort of see sort of in the bottom right-hand side of this picture here, there's these corners that it's pressed into. And so those corners specifically are meant to stop any sort of linear side-to-side motion that occurs.
Do you think that's sufficient?
Based off of our calculations, we assume it is, but we don't know until we have experimental data to back that up.
Yeah, so that's a great question, and we didn't consider the circumferential acceleration or movement, only the radial. So that's something we could definitely look into and perform some calculations to ensure. Now, I believe the reason we didn't opt for a recessed or a more rigid container is that although these are standard ANSI well plates, there is some variation in the dimensions. And so we decided that a spring, a radial spring would be the best way to accommodate these variations of a few millimeters, ranging from 4, 5, 6 millimeters in variation, depending on how the bottom lip of the well plate is shaped. But no, that's a great question. Something we should look into.
I'll step back for a little bit and let a couple other folks ask questions.
I just wanted to jump in and say, and I think Tom actually mentioned it in the chat. Whoever did an actual hand calcs for a cantilevered beam instead of doing an FEA of it, thank you, for the love of God, thank you for not doing an unnecessary finite element model and actually sticking to fundamentals and showing us that you know how to do proper engineering. I personally, I saw it, and then I saw Tom's message pop up, and I was like, I could not agree more with that message. I also want to echo the film cover being a really cool concept. I haven't seen it. None of the Mech 2 kids last semester thought of it. None of the Mech 3 kids thought of it to prevent sloshing. So great find, great catch, awesome thing. And I also want to give you guys kudos on including TRLs and actually understanding them. I think that was a huge problem last year. Everybody was like, oh, TRL2. And you guys were like, actually, it's a 4 or a 5 because these things it needs refinement for our specific application, but we know it's going to work because it actually works used in something similar to this. So great job understanding those. Now my one nitpick. Do you guys actually understand how big 66 inches is? What is the average size of what is the width of a standard biosafety cabinet hood that one of these might be installed inside of?
I believe that last time I checked that the maximum was about 3 feet, but that could be pushing it.
3 feet's pretty standard. You can get large ones that are able to have 2 people working in them that are about 4 to 4.5 feet wide. But they're not 5.5 feet. So just a consideration there. Like I said, I had to have something to ding you guys on after complimenting you. But yeah, I think it's a bit weight wise, 165 pounds, like weight wise, like 165 pounds, perfectly reasonable, but that width, it's big. So how could you guys shrink it down, I guess is my question now.
For sure, we can shrink some parts in the actual chambers themselves because we made them a little bit longer so that it could allow people to kind of, reach in with both hands if needed. But obviously, if we are going to be fitting this in a smaller size, a smaller length in general, we can for sure take some of the length from the chambers themselves. And also HVAC component, if once we make sure that none of the wires can't reach the power distribution board, we can for sure see if we can shrink that part as well.
Yes, sir. And also just to add to that, some of that residual space comes from in a previous design iteration. We were toying with the concept of having a liquid handling system move sort of back and forth between the compartments, and we needed to make space for this super overly complicated, intricate gearbox that we just ended up just throwing out. So there will be some residual leftover space from that as well.
Since you bring up the second compartment, I would suggest that if you don't have a requirement to run both well plates and conical tubes simultaneously, you could cut about half of your apparatus off right there if you just make it so that you could run either on the same shaker table.
Yeah, and that's definitely true. It would just be a trade-off with being able to run experiments with different environmental conditions.
Okay, any more questions from our panelists?
Hi, yeah, this is Sean Roslett with Cummins. I had a question regarding the shaker functionality and LED control. So you did mention that those were programmable and the user could pick between how many LEDs they wanted or what LED pattern, or if they wanted orbital or linear motion on the shaker functionality. So how does the user actually program those? What is that interface like?
That is a computer software that is coded that is going to be interacting with the Raspberry Pi and will be installed either on the user's laptop or on the PC. That's really more of a computer science question, but that Raspberry Pi acts as a controller that receives data from those components and sends it into the software so that the user can understand what's it currently spinning at, is it on or off, etc. And the user can enter their wishes or enter a pre-programmed experiment into that software.
Hey, this is Alexis from Cummins, kind of stemming off of Sean's question there. So are you saying that your visual indicators, showing the system on or off or elapsed process time would be something that they'd view on their computer screen? Or is there kind of a separate LED or screen on the side of your device that would show the user that?
It's all going to be handled from the computer screen. So we don't have like a digital interface or any like LEDs like on physical lights like on the side of the machine. It's all displayed through the software program that's been installed on the laptop.
Okay.
And I have another comment, maybe not as much of a question, but stemming from what Sean was talking about earlier with the width overall dimensions of the system. I think it would be very helpful if in the beginning of the presentation, you would clearly define what the customer requirements were. And that way it might even help you guys be able to more specifically mention how your design is meeting those customer requirements.
Yeah, it's good that you specify that because the actual maximum length that was required by customer needs was actually 72 inches. So the length that we have is actually much smaller than that. And regardless, even if it's not fitting into a BSC, which is BSL2 required, the inside of the chambers are sealed and controlled via those air check valves and whatnot, so that the environment in there will not interact with the environment outside at all, not until it passes through the laboratory HVAC system.
Yeah, but I would like to just follow up. I think that's a good presentation idea, though, just to include the customer needs to help both us and you guys that are viewing it connect those to our outputs.
Right.
Hey, just two comments and then a question. Do you have a chart showing the requirements fulfillment? Any kind of quick summary chart?
We do on our poster, but not on our presentation.
Okay, and during the presentation, I liked the video that showed that you that showed the animation with the fan to show, really help me understand the placement of the fan. And I do like the innovation for the self-sealing seal cover. So thanks.
We still got time, so I guess I can keep asking questions. How much time is it going to take your system to process? I believe from other groups, there's a requirement of I think 15 minutes to process a 384 well plate. How quickly can you do that between? Okay, you had the processing time there. Is that including like flow rates and motion of the system?
Yes, as well as ODFI measurements.
Oh, that's including. Oh, that's quick then. Okay. You can do 384 wells of like fluid service and optical measurements in 13 minutes.
Yes.
Wow. See what else is on my list. The actual photo sensor that you showed on the end of the I guess the cantilevered arm on the motor, is that hinged at the bottom?
No, so that was designed to be a rigid connection, so it would be a tight fit. Now, the reason it is not a solid beam is in the event that the sensor itself breaks for whatever reason, it's easily replaceable. So you could simply undo the screw and remove that sensing system, or if a wire comes undone. It was essentially made for ease of manufacturing because these are 3D printed parts. And for easy replaceability.
Okay, so this isn't designed to accommodate, or maybe it is, like to accommodate like different heights of well plates. I guess I'm not clear on why it's rotating out of the way here.
Sure. Let me see if I can find. There's a better picture that probably illustrates this. But because it's attached to our liquid handling system, yes, this bottom one on the left here. The arm itself can be seen in the bottom right portion of that image. And so in this position, it is in the measurement mode. And so it is the lowest point of our liquid handling system and can move up and down with that system to accommodate the different well plate heights or at the different tube heights. For example, if you have a tube filled halfway with medium, it would not be advisable to take a measurement at the top of the tube. You might want to move a little bit closer to the surface liquid. And so as you can see in this current orientation, if you went to insert this syringe into a well plate, you would certainly have interference with the measurement system with the surrounding environment. And so the motor there is designed to just rotate. It's a stepper motor, so we can rotate it 45 degrees, 90 degrees. And in this case, we would rotate it 180 degrees, completely vertical and out of the way so that all the liquid handling actions can be performed.
Okay. And while we have this this picture up on the screen, we've got a big old cantilever beam, complicated cantilever beam hanging off of your motion system here. I don't remember seeing a vibration analysis with your shaker motors going. Is that a concern that you're going to excite any natural frequencies here?
We haven't done a calculation to confirm that, but we don't expect it at least. But that might be a good thing to include in our final design report.
Yeah, I'd suggest doing that. What about contamination between like wells and the plates, between the different well plates? Do you have any sort of system to clean, flush out as you're delivering and removing fluid from each well?
So the contamination, it's partially from this film, so there's less of a risk of contamination between the wells, and then we also have this well of sterilizing solution within each chamber. So if the needle needs to be sterilized between going into each well or tube, it can come over here and sterilize with the solution.
Okay.
If you have to sterilize between wells, so which would probably be pretty common because if I'm taking a sample from one well to do something with it, I don't want to, go and sample my next well with the same needle. How much would that change your processing time?
I mean, I think that's a function of the experiment. The way that our time was calculated was based off of filling the wells and then measuring each ODFI. But I mean, depending on how many times you need to like remove material and insert it into each well, that would obviously change the processing time, but I think it's dependent on the experiment.
So I guess when you did your filling time, it was you had all your material on board all at once to fill the plate in one go, or was that okay? So you weren't taking, or is it traveling to pick stuff up, drop it, pick stuff up, drop it? Like
it included the times that it had to refill the syringe in order to fill all of the plates, but it did not include, I mean, going back and forth between every single well to fill and dispense.
Okay, we've got about 2 minutes left. If anyone has any final questions, if not, we can conclude a little early.
Yeah, I do have a couple more final comments. Overall, just want to say I thought this presentation was really great. I thought it looked very professional. You had a lot of great detail on there. Visual wise, I think you did a great job zooming in and really showing the details. However, for the first couple slides, I would recommend having a visual that maybe breaks down the different areas of your design and maybe shows some flow paths, kind of like an architecture overview of your design. Just a little bit more clear of the separate functionalities that you have. But yeah, overall, I thought it was really great.
Thank you.
Great. Okay, so if there's no additional questions or comments, let me stop recording. We'll wrap up there.